Oop, I don't want that. Okay, I guess we'll get started now. So we're moving out of inheritance, and we're moving into a topic called generics. All right, so remember we implemented a stack class, and we had a couple of them. So one of them was a stack of ints, and the other was a stack of strings. And so we had this class called int stack, or maybe just stack originally. Right? And so just to quickly remind you what was inside of a stack, right? This is an array-based stack. Right, in here, so this is the important part. Well, this is one of the important parts here. So right there, we have our array that holds our elements of the stack. Right, the type of the array is int because it's a stack that holds ints. Our push method, right, accepts an int as input, right, and pushes that element onto the stack. The pop method removes the top element of the stack, returning an int. Okay, now if you wanted a stack of strings, this doesn't work, right? So this stack only accepts ints, right, onto the stack, or you can only push and pop ints to and from the stack. So if you wanted a stack of string, you're kind of stuck at this moment, right? So before, Java introduced this mechanism called generics. One solution would be that you create an entirely new stack class. Right? So now you go and make your string stack class. Right, now remember, here's int stack. Right? But when you go and make string stack, what you very quickly realize is that almost nothing changes in your class. Right? So the name of the class changes, right? Because you can't have two classes with the same name. The array type changes, right? So it's now an array of string instead of an array of int. The signature of the push method changes. Right? So instead of taking an int as its element, it now takes a string. And now the pop method, instead of returning an int, it now returns a string. Furthermore, if you go in and look at the implementation of all the methods, almost nothing changes in the methods either. Right? And so in other words, well, actually, we're going to look at the pop method to see exactly what happens when you implement a stack of strings. Right? So it looks like what you can do is you can just copy the int stack class and then make a small number of changes to get a stack of strings. Right? If you go and look at the pop method, you can in fact confirm that that's the case. Right? The only two lines that change in the pop method are the method header, right? So it now returns a string, and then when you get the element from the stack to return it, that now changes to string. Right? And you can even get rid of that line there by returning this stack, square brackets, this top index, +1, I think. No, what would it be? Yeah, +1, right? So you can even get rid of that line there, and there would be even fewer changes, right? There would be literally no changes to the body of the method. Right? And when you look very closely at what's happening here, the only things that are changing are some type names, right? So that string, right? From int to string, right? From int to string, from int to string, from int to string, right? And that in the name of the class. Right? So basically all we're doing is we're substituting string for int in a few places. And now, so now if you want to make a stack of double, you do the same thing. You make a new class, you make a few changes, and now you've got a stack of double. Right? And you can do this for any type. Right? So if you wanted to make a stack of lists, for example, you would go in, make a few changes, change int to list everywhere, and away you go. Now it looks like this is purely mechanical. So it would be nice if you could get the compiler to do this for you. Right? So wouldn't it be nice if you just tell the compiler somehow, hey, look, I want a stack of something. Can you make me that class? And the answer is yes. And that's what generics are for in Java. Now it turns out this isn't exactly how it works, but it's close enough. Oops. All right, now generics weren't introduced into the Java language until the 5th version of the language. So they came in quite late, relatively late. In other words, the language had been around a long time before they introduced generics into the language. But this sort of thing is useful, right? It's useful to have a stack that can hold different types. And so there was a workaround before they introduced generics. Right? And so the idea was, instead of making a stack of int, or a stack of string, or a stack of double, you make a stack of object. Right? Because object can hold anything in Java. Right? In C, you would make a stack where the elements are stored as pointers to void, right? Because a pointer to void can point to anything in C. Right? In Java, you just use big O object instead. Right? So you can easily do this, right? Making the changes so for example, if you use the array list as your storage for the stack, it's trivial to do. It's trivial to do for the list for the array-based version too. You just change every int to object, and away you go. So here's our stack that uses a list, right? Instead of a list of whatever, right? List of int, we now just make a list of object, right? Instead of pushing an int, you push an object onto the stack, right? Instead of popping an int, you pop an object off the stack. So it's very easy to make this change, right? Now that you've got a stack of objects, you can push whatever you want onto the stack. Right? So I can now make a stack, list object stack, and if I want to, I can push a bunch of ints onto that stack. Right? I can make a list object stack, I can push a bunch of strings onto the stack. It's slightly inconvenient, right? Because it returns object every time. Right? So when you're using this stack, whenever you pop an element from the stack and you want to use that element for something, you have to cast that element to the type that you think you pushed onto the stack. Right? So if you pushed a string onto the stack, when you pop it back off, you have to cast the object to string. Right? So for example, here's my string stack. Right? But it's really a list. It's really a stack of objects. Right? I can push the string hello, konnichiwa, and hello onto the stack. Right? Everything works fine. Now the problem is when I want to do something with one of those strings, I have to pop it and then cast it to string. Right? Because pop returns a big O object. Right? And you cannot substitute big O object for string. Right? The other way around it's true, right? I can substitute a string for a big O object, but I can't substitute a big O object for a string. So now every time you pop something, you have to cast, which is inconvenient. Right? After the cast, you can go ahead and use a string method on the reference s. Right? So now you can write s to uppercase. Right? So that's slightly inconvenient, but it's still usable. Right? If you remember that if you remember that your stack is a stack of strings, then when you pop stuff off, it's relatively easy to do the cast. There's a more serious problem here, though, in that a list of object can hold, you can use an object reference to store anything, which means you can push anything onto the stack, not just one type. Right? So I can make a stack that's only supposed to hold strings, but there's nothing from stopping someone else from pushing something else onto the stack. Right? And there's no way for the compiler to help you, right? Because you told the compiler that this is a stack of object. As far as the compiler is concerned, you can put anything into an object reference. So it lets you do that. Right? So for example, I can make a stack. Right? It's supposed to be a stack of strings. That's why it's called string stack. Right? Push some strings, that's fine. You can push the integer 1 onto the stack. The 1 doesn't get converted to a string. It gets auto-boxed to an integer object. Right? So you now got a stack that's got 3 strings and an integer on it. You can make another stack, right, and push that stack onto your stack. So now your stack's got some strings, an integer, and a stack on the stack. You can make a data object and push that onto the stack. Right? And again, this works because all of these things are objects, and object is the superclass for all classes in Java. Right? So everything, all of these things that I'm pushing onto the stack, these are all substitutable for object. Now you've got a problem, right? So now when you try to pop stuff off the stack, you have to remember what was on the stack. Right? So now you have to remember, hey, the date's on top, the stack is second, the integer's third, and so on and so on and so forth, which is not workable, right? The whole reason you're making a collection is to avoid the point of having to remember what objects are on the stack, right? What types of your elements are on the stack. Right? So we call this a lack of type safety. So the fact that any type of element can be pushed onto the stack makes it impossible to write what are called type-safe methods that operate on collections of objects. Right? The problem is you can write the method. It will compile cleanly, but it will fail at runtime. So for example, I can make a method called sum and clear. Right? It takes in a stack, right? And it's supposed to be a stack of int, right? Because this method returns an int here. Right, so what this is going to do, it's going to pop all the elements off the stack, summing the elements as you go, and then return the sum. right? It's easy to write, right? While the stack is not empty, or while the size of the stack is greater than 0, pop the stack, right? Now remember, you need the cast because the stack holds object references, so I have to cast it to integer, right? And then add that to the sum, and then return the sum, right? Now the problem is, this stack here can hold anything, right? It says here, the name sort of suggests that it has to be a stack of int, but there's nothing from stopping someone from calling the method with a stack that's got other stuff on it, right? So for example, there could be strings on it. The problem with that is that when someone calls the method with their stack, and you pop the stack and then try to cast it to integer, the cast fails, and now your method throws an exception, right? So this method works, but you have to tell everybody that it's going to throw an exception if there's an element on the stack that's not an int, right? Or not convertible to int anyway, right? Not castable to integer. And that's, it's not just inconvenient, it's not type safe, right? In Java, so Java tries very hard to make things type safe, right? Type safety lets the compiler catch errors rather than the programmer catching errors at runtime, right? It's much better to catch errors at compile time than it is to have to run your program to find the errors, right? So can you get type safety and the ability to create collections or objects having some specified type, right? And so the answer is yes. So the facility that lets you do that are called generics, right? So generics in Java let you parameterize a class or an interface or a method over types. Right? So what that means is you can make a class, and one of the variables that you have to tell, one of the variables of the class is the type, is some type, right? So for example, when you make a list or an array list, right, you have to tell it that what type of element you want on that array list, right? So you have to make an array list of string, for example, right? So the type that you've been putting into the in between the angled brackets, right? That's what's called the generic type, right? And so the benefit of doing this is that instead of making all these separate classes, right? Int stack, string stack, date stack, right? Someone else might have to make some my type stack where my type is some type that they care about, right? This lets you make just a single class, and anybody can use the class as long as they specify the type of their, as long as they specify the type parameter, right? So you would like to be able to write something like stack integer, and that makes a stack that can only hold integers, right? You'd like to be able to write stack angled bracket string angled bracket, and that lets you make a stack that only holds strings, right? Similarly, you'd like to make a stack of dates that can only hold dates, right? And you want to do this without having to make these 3 separate classes over here. And so these generic classes are type safe in Java, are almost completely type safe in Java. So in other words, if you make a stack of date, the compiler will test or will check if you're actually, if someone is using the stack of dates to only push dates onto the stack, right? The compiler will not let another programmer push some other element type onto the stack. Okay, so if you want to make one of these classes, then it's relatively straightforward. You have to get used to the syntax, right? So when you declare a generic class, right, it's the same as declaring a regular class, right? So you write class name, except now you write the angled brackets, and then the types, the type parameters separated by commas for the types that are important to your class. Right, so you'll see what I mean about this in a second. The angled brackets denote what are called the type parameter section. Right, so these are your type variables, right? T1, T2, whatever are type variables here. You can give these names, you can give these type variables different names. For the generic types in Java, these types have to be non-primitive. Right, so that's one of the limitations of generics in Java. So T1 can't be int, for example. T2 can't be little d double, and so on and so forth. So they have to be reference types. Okay, now these names here, so you can use T1, T2, T3 if you want. You can use whatever name that you want. Right? But there is a suggested naming convention. So if you're making a collection, which is what the generic types are commonly used for, right? List, set, map, right? So you're making something that stores elements, then normally the generic type is given the name big E for the element type. The generic types are also normally given 1 or 2 letter names. Right? So the type parameter is normally very short. Right? For maps, key and value are normally used. Right? If you have some sort of numeric type, so in other words, you want to make a collection that can only hold some sort of that can only be parameterized over numbers, then you often use the name n. Right? And then if you just want some generic type name, it's often just T. Right? So T1, T2 through T3 is not uncommon either. All right, so let's look at a simple example of making a generic class. So this is going to be the world's simplest generic class. Right? So the Java methods only return a single value. Right? That's often inconvenient. Right? If you have a method that searches for the max or the min of an element in a list, right? Often you want to know what is the maximum or minimum value, and you want to know where is that value in the list. Right? So you actually want to know 2 things. If you sort a list, sometimes you often want the sorted list back, right? But then you also want to know where were the elements originally before you sorted the list. Right? If you use MATLAB, MATLAB actually tells you that information. Right? So often you want 2 values back. Right? Sometimes you want 3, sometimes you want 4. Right? But you can trivially make a generic class that lets you represent 2 values. Right? And you don't even need any constructors or methods in this class. Right? So I can make a class called pair, right? That holds 2 values. Right? My values are called first and second. Right? It's generic. Right? So I have types T1 and T2. Right? The type of first is T1. The type of second is T2. So someone can make a pair of string and double, right? And then first its type will be string, and second its type will be double. Right? Someone can make a pair of list of integer and say set of integer, right? Then T1 will be a list of integer, and T2 will be a set of integer. Right? So to write the max method that finds the maximum element of a list T and also returns the index of the maximum element, right, I can now return a pair. Right? If this is a list of integer, then my pair will be integer, integer. Right? The maximum value, I think the maximum value. Result first, yes, no, hang on, sorry. The first type is going to be the index type. The second type is going to be the element type. So I make my result, which is just a pair. Right? I can write result.first equals 0 because first and second are public, so I can access them directly. Right? Result second is equal to the first element of the list, so I'm going to assume that the maximum element of the list is the first element. And then I'm just going to loop over the list looking for bigger values. Right? So for the rest of the list, get the element. Right? If the element is greater than the current maximum value, right, then set result first equal to I, so that remembers the location of that element in the list. Right? And then remember what the current maximum value is. Where is max defined? It's not defined. Sorry. That's going to be result dot second. Okay, so result dot second is holding the current maximum value. Right? So if you find an element that's bigger than the current maximum value, set result second to that element, right? And remember what the index is. Right? And so when you return that pair, that gives back the caller the location of the maximum element and the value of the maximum element. Right? And so there's an example of making a very simple generic type. Right? Now, this is just a class, so you can have constructors, you can have methods, you can have other fields. Right? Your fields don't have to be generic. Right? So in other words, if you're making a class, if you're making a generic class, right, some of your fields can be of the generic type. Other fields can have whatever type they need. Right? There's no reason that everything has to be generic in a generic type. Okay, so if I want to turn our stack class into a generic class, it turns out it's very easy. Just a second here while I flip through. Okay, so I want to turn our array stack class into a generic, which used to only hold ints or strings, I don't remember which. Right? I want to turn it into a generic class, right? So that it's an array stack that can hold any element type. Right? So the first thing you do is you add the generic type specifier to the end of the name of the class. Right? We use the type name E. We use the type name E because this is a stack is a collection of elements. Right? So normally, if you have a collection of elements, the type name is E. Right? And then everything else looks straightforward. Right? So everywhere where we used to have, I think, string, you just change it to E. Right? So instead of having a array of string, it now becomes an array of type E. Right? We've still got our top index. We don't have to change its type. Right? Its type is int, so it doesn't have to be the same as the generic type. Right? Now, when you go to implement the constructor, this is where you run into your first problem. Right? So in your constructor, we have to make this array of this array. Right? So what you would write is what you want to write is new, and then the element type. Right now, our element type is generic. Right? So we'd write E. Right? Square bracket size of the array that you want to create. Now, if you write that, the compiler will tell you that that's an error. Right? So in Eclipse, you'll get this red underline saying, hey, you can't make it a generic array. Right? Which is unfortunate, because this is really what we want to do. Right? So that line that's highlighted on that slide causes a compilation error. Right? In Java, you can't make an array of generic type. So this is one of the limitations of Java's generic facility. Because it was added late to the language, it was very hard to add this facility and still also allow the creation of generic arrays. Right? So you can work around this, right? And the way you work around it is you just make an array of object instead, which is more or less what we did previously. Right? Previously we had a list of object. Right? Now I'm just going to make an array of object instead, because you can make an array of object in Java. Right? Okay, so no problem. So you go back, right? You change your array, so its type is now big O object. Right? Now in my constructor, I can make that array without any issues. Right? So the compiler doesn't complain. Right? This is in lab 6 and 7 if you've done it already. Right? So arrays are interesting in Java. So arrays existed from day one in the Java language. So they're a bit special. Right? Arrays in Java are said to be covariant. Okay? So if you have, if sub is a subtype of super, right, then it turns out in Java, if you have an array of sub, you can use that when you need an array of super. Right? In other words, an array of sub is considered to be a subtype of an array of super. Right? So if you have an array of object, if you have an array of string, then string is considered to be inherited. An array of string is considered to be inherited from an array of object. Right? And so that's what it means to be. That's what it means when people say that arrays in Java are covariant. Right? An array of a subtype is substitutable for an array of a supertype. So does the following compile? The answer is yes. Right? An array of integer is substitutable for an array of object. Right? So you can store an array of integer in a variable whose type is array of object. Right? So that compiles. Right? Does that compile? The answer is yes. Right? Which is unfortunate. Right? So you've made an array of integer. Right? You stored that array of integer in a reference, right, in a variable whose type you've told the compiler is an array of object. Right? So when you store a string in the array objs, right, the compiler can't detect that this is an error. Right? Because you told the compiler that objs is an array of object. Right? Objects can hold anything, which means you can put a string into this array objs, or into the array referenced by objs, even though that array actually refers to, or actually is, an array of integer. Right? So unfortunately, this compiles, which you really don't want, because this is not type safe. Right? Right? Does it run cleanly? The answer is no. Right? So when you actually try to run the program, this is when the program fails. Right? Which is what you don't want to happen. Right? You want to catch this error at compile time. Right? Okay, now generics are generics are invariant. Right? Arrays are covariant, generics are invariant. Right? So in other words, if you make a generic type like list, right? If you have a list of object and a list of string, a list of string is not considered to be a subtype of a list of object, right? So in other words, that thing there is not substitutable for a list object, right? So for any two distinct types, T1 and T2, right, there is no relationship between a list of type T1 and a list of type T2, right? There's no relationship other than the fact that they're both lists, right? So there is no inheritance relationship between those two types. Right, and so that's what people mean when they say that generics are invariant. So does the following compile? The answer is no, right? Yes, the answer is no, right? The Java compiler will stop that immediately, right? Because an array list of integer is not substitutable for a list of object, right? For this to work, that would have to be big O object, right? So that doesn't compile. Okay, now what about the rest of the stack class? Well, we have to implement push and pop, right? And that's all we have to do, so it's very easy, right? So what does push look like? So ignore all this stuff up here, right? All this stuff's just reallocating the array, right? Ignore this stuff here. The important thing is this line here, right? So the only change that you have to make is when you copy the array, right? So before, we were copying an array of int. Now you're copying an array of object. What do I have to store it in? I have to store it in an array of object now, right? Instead of storing it in an array of int, right? And that's it. There's actually no change other than that. There's one change here, right? So change the parameter type to E because you're pushing an element of type E onto the stack, right? Other than that, there's nothing to change, right? This line here compiles cleanly, right? That compiles without any issues because this stack is an array of object, right? You can store anything in an array of object. So you can store whatever element this is, regardless of its type, into that array. So there's no change that you need to make here. So that was easy. Now what about pop? Pop, there's only two changes you have to make. Well, I guess three, depending how you count, right? So now pop's going to return the generic type, right? So it's going to return an element of type E, right? So my return value has to also have type E, right? Because that's what I'm saying I'm returning. Now, when you get the element from your array, right? So our array is an array of object, right? I cannot store an object reference in a variable whose type is E, right? So object is not substitutable for E, right? So now I have to cast, right? So round bracket, big E inside, casts whatever that is to type E. Right? And now you can store that in the variable element, right? And that's the only change you have to make, right? So converting your stack of string So converting that stack implementation from a non-generic type to a generic type is almost trivial, right? It's very easy to do. Right? Now, what about the interface? Well, the interface is even easier to do, right? So remember we made an interface for stacks, right? If I want a generic stack class, then it makes sense to turn the interface into a generic type as well, right? So our previous stack interface was for stacks of strings. If I want to turn it into a generic type, I just change every string to E, right? So here's our original interface for a stack of string, right? So when you push an element, it takes a string. When you pop an element, you get a string, right? To turn it into a generic interface, all you do is the following, right? Add the generic type, right? Change string to E, right? And change the return type to E. That's it, you're done, right? So converting a class or an interface from some fixed type to a generic type is often very easy, right? Usually the changes are almost just cosmetic, right? You're basically just swapping in some types. Okay, the last thing you have to do is you now want to take your ArrayStack class and convert it so that it's now generic, right? So now you want to say that it implements, now you want to say that it implements the generic stack interface, right? So our ArrayStack E, right, now implements the stack E interface, And you've now got a fully generic stack implementation along with a fully generic stack interface. Whoops. Oh, that was short. You want to go or you want to do the next lecture? It's up to you. I don't care either way. You get the vote. Stay, go. Who wants to stay? Okay. I heard one stay, so we'll go with stay. That means I have to update OnQ quickly so that you've got access to this lecture. I'll give you 1 second here. Right there, and I need to do this. This is nope. I have to fix the numbering later on, but that's fine. Oh, okay, let's do this. Okay, I don't think we talked about queues in this course, although you've probably seen them from your previous course, your data structures course. Did we? No, we didn't talk about queues. Okay, so here's an example of a queue. Oh wait, we did? No, we didn't talk about queues in this course. Okay, so here's an example of a queue. A queue is just a line, right? So you've got a front of a queue, you've got a back of a queue, right? When you get into the queue, you enter at the back, right? When you leave the queue, you leave at the front, right? Unless you have like VIP status or something like that, right? When you can jump the queue, right? That's called a priority queue in computing science. Here, we're just implementing a plain old queue, right? Queues are like stacks. They only have 2 operations, right? So you have NQ, that's when you get into the back of the queue, and you've got DQ, so that's when you remove an element from the front of the queue, right? You can have other operations as well, right? So a queue is a collection of elements, so it's often useful to know how many elements are in the queue, right? It's often useful to know, is the queue empty? Sometimes you want to look at what the element that's at the front of the queue without taking it out, right? So peek gets the front element without dequeuing it. Contains is a bit odd, but you might want to know if a queue contains an element of some type, of some value. Okay, so this is what a picture of a queue looks like. So if you start out with an empty queue, right? Notice I've got these things F and B. So F points at the front element of the queue. B points at the back element of the queue, right? If there's no elements of the queue, then they both point at the same place, which is nothing, right? So they're both null in this case. If you NQ an element onto this queue, right, the front and the back of the queue both point at the single element that's in the queue, right? If you NQ another element, right, front still points at the front, but B now points at the last element of the queue, right? And so on, right? And so on, and so on. Does this move by itself? No, it doesn't move by itself. Okay, so on, right? Now, when you DQ, elements come out at the front, right? So when I DQ the queue, right, I'm going to get back the string A, right? And then either the elements in the queue shift forwards or you shift F to the right. You can think of it 2 different ways, right? But now F points at the new front element of the queue, right? Notice B doesn't change, right? DQ again, right? The B comes out. Let me back that up. Okay, DQ again, right? The B comes out, and then F moves so that it points at the front element of the queue, right? If this is a physical queue, then everybody walks up the front of the queue, right? Same thing. The animation time is a little too slow. All right, one more time. All right, now notice when you notice that when you DQ one more time, right? F and B both change in this case, right? So F and B both point at nothing now. Previously, whoops, sorry, right? Previously, B always pointed at the same element, right? So if there's stuff in the queue, B always points at the same element. But when you empty out the queue, you have to update B, right? Okay, so queues are what are called FIFO data structures, so first in, first out. Right? The first element that you put into the queue is the first element that comes out of the queue. Right? The last element that you put into the queue is the last element that comes out of the queue. Right? So they're also called last in, last out. Right? And it turns out they're used all over the place in computing science. Right? Any website that you use where you buy stuff from it, there's a queue of some sort on that web server. Right? Because lots of people, or more than one person, can be trying to buy something at the same time. Right? And so they put all the requests into a queue, and then they serve up they service each request one at a time. Right? And this is true of web servers in general. Right? So if everybody's trying to access some website at the same time, right, the requests for access are serviced in the order that they arrive. Right? Queues in operating systems they appear all over the place. Right? So an operating system is basically responsible for managing resources of your computer. Right? There's lots of processes that might want access to a resource at any one time. All of those requests go into some kind of queue. Right? So you have printer queues, you've got disk queues, you've got CPU queues, you've got network queues, you've got all sorts of queues. Right? And then there's a bunch of algorithms that are also implemented using queues. I assume you're going to take an algorithms course at some point. And so at that point, you'll learn about algorithms which are easier to implement if you have a queue data structure. Oh, there's a whole branch of mathematics devoted to this called queuing theory. Any of you electrical engineering? Anybody? Okay. You'd also see queuing theory in electrical engineering if you do any network stuff. Yeah. Okay. So we can make an interface for queues, just like we had an interface for stacks. Right? I'm going to start out by making it generic right away, so I don't have to do the conversion later on. So I'll make an interface for queues that can hold any element type. Right? Our interface is straightforward. We've got size, right? Number of elements in the queue. We have isEmpty. We can make isEmpty a default method, because to implement isEmpty, all I need is the size method. Right? So I'm allowed to implement a default method, you are allowed to use the methods of the interface. So we can make that default so that people who implement the interface don't have to implement isEmpty themselves. Right? We've got enqueue and dequeue. We've got two methods that look at the front and back element without doing anything to those elements. Right? So that they don't remove the element from the queue. Okay, you can implement the queue with a list, right? Just like we did with a stack. So a queue implementation using a list is similar to that for a stack, except for dequeue, right? So when you enqueue an element into the queue, we're going to add the element to the back of the queue, right? When we dequeue the element from the queue, we're going to remove the element from the front of the list, right? It's trivial to implement this queue. Internally, you have a list, right? So we're going to use composition, right, to store a list. The list is going to hold the elements of our queue. I'm just going to call the queue, the list queue, right? Constructor, what does the constructor need to do? Well, it needs to make a new list of some kind, right? So I'm going to make a new array list, which turns out to be a bad choice, as I think you'll see, right? Size is easy. You just return the size of the list. Enqueue is easy. You just add the element to the end of the list. Right? Dequeue is easy, right? If the queue is empty, I'm going to throw an exception, right? So I've got a little I've got a little validation method here that's private. It does nothing but test if the queue is empty and throw an exception if it is. Right? So if the queue is empty, throw an exception. Otherwise, remove the first element from the list. Oops. Why are there two things here? Remove the first element from the list and return the removed element. Right? Now the problem with this implementation is that when you remove the first element from an array-based list, you end up with complexity big O-N. Right? Because in an array-based list, when you remove the first element, you have to move all of the remaining elements forward one position in the array. Right? So that's not good if you need a fast queue. Front is easy. If there's no front element, throw an exception. Otherwise, return the first element of the list. Back is easy, right? If there's no elements in the queue, throw an exception. Otherwise, return the last element of the list. ToString's easy. You just return the string representation of the list. Right? So this is dead easy to implement. You now have a working queue in like 2 or 3 minutes of coding time. Okay, now the fact that removal and additions occur at different ends of the queue make implementing this thing with an array tricky. Right, so we want to do the same thing that we did with the stack. Right? With the stack, we started with a list-based implementation, then we went to an array-based implementation, then we went to a linked node-based implementation. So we're going to do the same thing. The problem is when you use an array, things get a little bit tricky. The advantage is when you use an array, you don't have to pay the ON cost when you remove the element from the front of the queue. So that's nice. Right? There's another operation here that's ON. Where's NQ? Oops, sorry. Hello? NQ. When you add an element to an array-based list, right, every once in a while that operation is big ON. Right, so your worst case complexity of an NQ and DQ in this implementation is big ON, which you want to avoid if you can. Right? So if you want to do this with an array, you can avoid the big ON cost for dequeuing, right? Which might surprise you because when we did it with a stack, the array and the list-based implementations were basically the same. Right? So to do this, I need 4 fields. Right? I need the array to store my elements. Right? I need to know what the size or the number of elements in the queue are. Right? And I need front and back. Okay, so front is going to be the index of the element that's currently at the front of the queue. Right? And back is going to be the index of the element currently at the back of the queue. Right? So there is a picture of an empty queue. Right? I've got an array of size 16. Right? Front is the, I guess front is going to point at, what does it say exactly? Front is currently at the front. Okay. So front is going to point at the index whose value is 0. Right? Back is going to point at the index, at the element whose index is -1. Right? So in other words, the back is not a valid index for this queue. Right? So that's how we're going to implement. This is how we're going to implement the empty queue. Right? Okay. Now, when you NQ an element, right, this is going to be similar to pushing an element onto the top of a stack. Right? So when you NQ an element, you have to check, is there space in the array to hold the element? Right? So if the array length is equal to the size, right, then you need to make a new array with greater capacity, copy the old elements into the new array. Right? So I know I have to resize the array, right, because I'm out of space. I'm going to move back 1 position to the right. Then I'm going to set the element at array back to the NQ'd element. Right? So there's a picture. Right? So if I NQ the A, right, I'm going to move back 1 element to the right. Right? So it used to be -1, so it's now 0. Right? I'm going to set the array element at that index to the element that we've NQ'd. Right? So in other words, set the element at array index 0 to the A. Right? If you do it again, right, advance back 1 position, and then set the element that back is pointing to the NQ'd element. Right? We can do it again and again a few times. Right? So now I've got a queue of size 5. Right? So all that's happening here is that back's moving, right? Because that's what NQ does. Right? You don't normally have to adjust the front of the queue when you add a new element to the queue. Okay, now what about DQ? So to DQ, I need to remove that A from the queue. Right? I want to return the A, and then I want to adjust the front of the queue so that the front of the queue points to the next element in the queue. Right? So I want to remember what that A is. Oh, sorry. I want to remember what that A is. I want to shift front 1 position to the right. Right? What else do I want to do? I want to null out that element. I'll explain why in a moment. And then I want to, it's missing here. There's a couple things missing here. Step 4, increase the size of the queue by 1. Step 5, I guess step 3.b, decrease the size of the queue by 1. Right? So in other words, to dequeue the element, I want to remember what the element is at the current front of the queue. Right? I want to null out the element that's sitting at the front of the queue. Then I want to move front one position to the right, and then I want to return the element. Right? So to dequeue the A, right, I'm going to remember what the A is. Right? I'm going to move front one position to the right. I'm going to remove or null out the element that was sitting in position 0, and then I'm going to decrease the size of the queue. Right? So do it again, right? And again, and 2 more times, right? Notice here that when you remove an element from the queue, right, we're not shifting the elements in the array forward by 1, right? So you avoid the big O(n) cost of removing an element from the list, of an array-based list, right? So when you use just a plain old array, dequeue now becomes big O(1), right? Because all you're doing is shifting front. That's all you have to do, right? So if you dequeue 4 more times, you end up with a queue of size 1. Right? There's only the E in the queue. Now, if you dequeue 1 more time, right, you end up with the following picture. Right? So remember, whenever you dequeue, you're going to shift front to the right 1 position. Right? And we're now back in this situation here. Right? So back, right, is 1 position to the left of front, right? Which looks like maybe you can use this to test if the queue is empty. Right? But it turns out that's not true. Right? Okay, enqueue 1 more time. Right? So when you enqueue an element, back is going to shift to the right. Right? And it does, right? So there it was, you shift it to the right, set the element at back. Right? Keep on going. Right? You've now got a queue. Back now points to the last element of the array. Right? Okay, is the queue full? The answer is no. Right? You've got all this space over here, right, where you can add more elements, right? Okay, so what happens if you enqueue another element, right? Well, all you do is you shift back 1 position to the right, right? So it falls off the end of the queue. When you fall off the end of the queue, you just wrap around to the front, right? So you wrap around to the front, and away you go, right? So notice that back, which is supposed to be after front, right? If you look at the value of the indexes, right? So front is 5, back is now 0, right? Back is less, the value of back is less than the value of front, right? So it can be the case in this implementation that back is not always greater than front, right? Even though back is supposed to be the element, is supposed to be the index of the element that's at the back of the queue. Right? And you can keep on going. So when you reach, right, so when you filled in every element of the array, that's when the queue is full. Right? Now notice when the queue is full, back is 1 position to the left of front. Right? So a full queue looks like an empty queue if you just look at the values back in front. Right? That's why you need to keep the value size around. Right? Because there's no reliable way, just by looking at back in front, to determine if the queue is full or empty. Right? So we have to keep the size of the queue around as a separate field, right? That's why you need that 4th field. I just want to quickly, okay, so let me get to that slide and then we'll call it quits for today. Okay, so you can do the same, so the same thing happens with front, right? So if I dequeue a bunch of elements, right, front's now at the end of the array. If you dequeue the P, front just wraps around to the front of the array again, right? So front and back are both circular quantities. Right? They just keep on going around and around and around in the array, right? Which means you can draw the queue as what's called a circular array, right? So that queue there, QRSTU, is that circular array right here, right? So there's 16 elements in this circular array. Q's here, U is here, right? So front is there, back is there, right? When you view this as a circular array, front and back just keep going clockwise. Right? So enqueue an element, back rotates clockwise by 1. Right? Dequeue an element, front moves clockwise by 1. Right? And this it just goes around and around in a circle. Right? Okay, so we'll look at the details of implementing this array-based queue in the next lecture. Any questions? Super. See you, I guess, 2 days from, no, tomorrow. Right? Yeah, we'll pick up the implementation tomorrow.